Cellular manufacturing is a method of producing similar products using cells or groups of team members, workstations, or equipment to facilitate operations by eliminating setup and unneeded costs between operations. Cells might be designed for a specific process, part, or a complete product. They are favorable for single-piece and one-touch production methods and in the office or the factory. Because of increased speed and the minimal handling of materials, cells can result in great cost and time savings and reduced inventory. Cellular design often uses group technology, which studies a large number of components and separates them into groups with like characteristics, sometimes with a computer's help, and which requires the coding of classifications of parts and operation. Cellular design also uses families of parts processing, which groups components by shape and size to be manufactured by the same people, tools and machines with little change to process or setup. Regardless of the cell design, either straight line, U-shape or other, the equipment in the cell are placed very near one another to save space and time. The handling of materials can be by hand, conveyor or robot. A cell supervisory computer must be used to control movement between equipment pieces and the conveyor when robots or conveyors are used. A cell is a combination of people, equipment, and workstations organized in the order of process flow to manufacture all or parts of a production unit. Now, there is a little distinction between a cell and what is sometimes called a flow line. However, the implication of a cell is that it has one piece or very small lot or flow. It is often used for a family of products and has equipment that is right-sized and very specific for this cell. It's usually arranged in a C or U shape so that the incoming raw materials and outgoing finished products or goods are easily monitored. It has cross-trained people for flexibility. The objectives of cellular manufacturing includes the following. First, to shorten manufacturing lead times by reducing setup, work part handling, waiting times, and batch sizes. To reduce work in process WIP inventory. Smaller batch sizes and shorter lead times reduce work in process. To improve quality, accomplished by allowing each cell to specialize in producing a smaller number of different parts. This reduces process variability. To simplify production scheduling, instead of scheduling parts through a sequence of machines in a process type shop layout, the system simply schedules the parts through the cell. To reduce setup times, accomplished by using group tooling, which includes cutting tools, jigs, and fixtures that have been designed to process the part family rather than part tooling, which is designed for an individual part. This reduces the number of individual tools required as well as the time to change tooling between parts. Steps to implementing cell manufacturing. After you've mapped your value streams, you are ready to set up continuous flow manufacturing cells. Most cells that have been set up in the past 10 years do not have continuous flow. Most changes to cells have been a layout change only. That is, machines were moved in the cellular arrangement and nothing more was changed. A change in layout alone does not create continuous flow. Now, You decide which products or product families will go into your cells and determine the type of cell. For instance, is it product focused or group technology or mixed model? For product focused cells to work correctly, demand needs to be high enough for an individual product. For mixed model or group technology cells to work, changeover times must be kept short. The next step you take is to calculate takt time. Takt time, often mistaken for cycle time, is not dependent on your productivity. It is a measure of customer demand expressed in units of time. Takt time is equal to available time minus time per shift all over customer demand per shift. For instance, work time per shift is equal to 27,300 seconds and demand per shift is equal to 690 units. Then takt time is equal to 27,700 all over 690, which gives rise to 40 seconds. The implication of that is that the customer demands 1 unit every second. What if your demand is unpredictable and relatively low volume? Typically, demand is unpredictable. However, aggregate demand, that is, demand of a group of products that would run through a cell, is much more predictable. Tax time should generally not be adjusted more than monthly. Furthermore, holding finished goods inventory will help in handling fluctuating demand. The next step is to determine the work elements and time required for making one piece. In much detail, document all of the actual work that goes into making 1 unit. Time each element separately several times and use the lowest repeatable time. Do not include wasteful elements such as working and waiting time. Determine if your equipment can meet task time. Using a spreadsheet, determine if each piece of equipment that will be required for the cell you are setting up is capable of meeting task time. Third, create a lean layout. More than likely, you will have more than one person working in your cell. This depends on task time. However, you should arrange the cell such that one person can do it. This will ensure that the least possible space is consumed. Less space translates to less working, movement of parts, and waste. U-shaped cells are generally best. However, if this is impossible due to factory floor limitations, other shapes will do. For example, I've implemented S-shaped cells in areas where a large U-shaped cell is physically impossible. Balance the cell. This involves determining how many operators are needed to meet task time. Here is an example. Number of operators is equal to total work content over task time. That is the formula for getting the number of operators. And here is an example. For instance, let's say we have total work content to be equal to 49 minutes. Determine how the work will be divided among the operators is the next step. There are several approaches. Some include firstly splitting the work evenly between operators, having one operator perform all the elements to make a complete circuit of the cell in the direction of material flow, then reversing the above, then combinations of the above. Now, after you've determined the above 7 elements, you will have gathered much of the necessary data required to begin drawing and laying out your continuous flow manufacturing cell.